Hello students, welcome back to my channel Physics by KC. So in the last class, in the previous video, we discussed the entire blueprint of the chapter current electricity. Now we are going to discuss what actually the things that are related to resistance. What is a resistor and what are the things that are related to resistor. We will take a detailed blueprint on this resistance. So now the topic is resistance and resistor. What actually the resistor is. So in general, resistance means opposition created against the flow of charges, against the flow of charges. So resistance is a property which is not encouraging the flow of charges. It restricts, it resists, it stops the flow of charges. So that property we can say it as resistance, and that element whatever produces this resistance is called a resistor. So here resistance is a property and a resistor is the element which produces this resistance. So one thing we have to consider, a resistor can be represented like this. In standard notation, 3 peaks upwards and 3 peaks downwards. This is a resistance. And the units of the resistance is ohm, which is represented by the symbol ohm. This is the symbol. So, and one more thing what we have to discuss is resistance R can be represented by R is equal to rho L upon A. This is the first formula that we have to read here. R is equal to rho L by A. Here R is resistance and rho is specific resistance or resistivity, and L is length of the conductor and A is cross-sectional area of the conductor. So this is the basic thing that we have to consider. And second thing, how the quantities that can influence the variation in resistance of any material. So resistance in the sense, not only we can expect in case of a resistor, it is possible even in case of conductors also. Every material which will allows electric current consists of this resistance even in a very small amount, because no conductor is an ideal conductor. So each and every conductor is also having this property resistance. Now how we get variation in resistance value in accordance with the dimensions of a material or a conductor. For example, let us take a small wire of uniform dimensions. Its length is L and its cross-sectional area is A. Length is L and cross-sectional area is A. So the resistivity or the specific resistance of this particular conductor is rho. So from that we have written the formula R is equal to rho L by A. So the quantity, either the length or the cross-sectional area, that is going to influence the value of resistance. So the resistance value is going to change in accordance with the variation in these two quantities, either cross-sectional area or the length. But one thing we have to consider. See, if two lengths were multiplied, we are going to get area. In general, the mathematic notations, if two lengths gets multiplied, obviously we are going to get an area. If 3 lengths gets multiplied, we are going to get volume. Or else, if area is multiplied by length, we are going to get volume. So no matter whether a given wire that was shortened and the cross-section area is increased and the length gets decreased, but end of the story we will get equal amount of volume. The volume of that particular conductor is not going to change. For example, the question is in this way. Keeping the volume of a conductor constant, a conductor wire, its length gets decreased. Initially the length was one quantity and that length gets decreased. Then what happened to the resistance of the conductor? See, initially the conductor is like this. Its length is L1 and its cross-sectional area, this is A or A1. After that, its length gets decreased. Length gets decreasing means obviously the cross-section area is going to increase. Now the cross-section area is A2 and length is L2. Now what happens to the resistance value? This is what they were asking. Already we know resistance R is equal to, we can write it as rho L upon A. So when the length is M1 and cross-section area is A1, by that time resistance R1 can be written as rho L1 upon A1. Rho L1 upon A1. So clearly what they were saying is volume is constant. Volume is constant. So from this formula we can eliminate volume because volume is constant. How we can do this? If I multiply this with a L in the numerator and in the denominator, obviously what I am going to get? Rho L square upon A into L, we are going to get V. So from this relation what we can write here R is directly proportional to L square. If it is R1 is equal to R1 is proportional to L1 square and R2 is proportional to L2 square. Now R2 by R1 is equal to L2 square divided by L1 square. So this is the relation that we got. When the volume is constant and there is a variation in length, either that length gets increased or the length gets decreased, on that particular occasion we can use this relation. R2 divided by R1 is equal to L2 divided by L1 whole square. So this is what we got. So when it comes to the properties of resistance, we can use this formula also. So we can write this formula. So in the blueprint of the resistance, we can write it as R1 divided by R2 is equal to L1 square divided by L2 square. So when we can use this formula? When volume is constant. Very good. And the next case, if the radius of the wire gets changed, if the radius of the wire gets changed while we are extending the wire or while we are compressing the wire, what happened to the resistance value? See. So this is a wire, this is length is L and the cross sectional area is A and radius of curvature is R. Then from this we can formulate one relation. R is equal to rho L upon A. So from this what we can write? This cross sectional area should be as a circle, so that we can write it as rho L upon pi R square. Otherwise, I just want to eliminate completely. They were not mentioning about length. They were saying radius gets changed. While we are changing the dimensions of a wire, the radius completely changed. What happened to the resistance value? So that there is no need of this L, there is no need of this rho, there is no need of this A. I just want to convey my relation only with R only. So I will change the relation like this. For example, if I multiply this entire relation by A and I will divide it by A. So automatically what is going to happen? Rho L into A, I can write it as V divided by A square. Okay. Now rho is resistivity. We are not changing the material of this conductor. And then V is the volume of the conductor. It is never going to be changed no matter either you increase the wire, the length of the wire, or you decrease the length of the wire. So that R is inversely proportional to A square. Very good. As we said earlier, this is R is inversely proportional to pi R square. Right. Now the question is A square. Now we have one more square. So I can write it as R is inversely proportional to R power 4. From this what I can write? If R1 is the initial resistance and R2 is the final resistance, then I can write as R2 by R1 is equal to R1 power 4 by R2 power 4. This is also one of the important relation. So the next quantity that we have to mention in this blueprint is when the radius of the wire gets changed while we are extending a wire or we are compressing the wire, then the relation of the initial and final resistance we can write as R2 upon R1 is equal to R1 by R2 whole power 4. Very important formula for objective point of questioning. Right? Okay. Right. So in this we can take one more relation, combination of resistors. So in the combination we have either series combination or parallel combination. This is first case, this is second case. So what is series combination? For example, if two resistors were joined one after another, this type of combination is called series combination. If one end of one resistor is connected to the same end of another resistor, so this combination is called parallel combination. If this one is R1 and this one is R2, this one is R1 and this one is R2. In case of the series combination, the resultant equivalent resistance can be written as R1 plus R2. In case of the parallel combination, the equivalent resistance R equivalent can be written as 1 by R1 plus 1 by R2. Okay. So these things we got from the relation V is equal to IR, that is Ohm's law. From this R is equal to V by I, here potential difference is same and the currents get splitted. So all these quantities that we are going to discuss in detail when we went to that particular concept. Now it is only group linked, that's why I am giving what are the things that we have to cover in case of resistance. So we can add these two formulas also. So series and parallel combination, so that I can put here in case of series R equivalent is equal to R1 plus R2 and so on. In case of parallel, R equivalent is equal to 1 by R1 plus 1 by R2 and so on. Right, we got one more point. Okay, so this is one end and thereafter we have one more important thing. So from this relation also we can write one more formula. So as we discussed earlier, the conductance is inverse of resistivity. So sigma is equal to 1 by rho. So obviously we can write it as R is equal to L by sigma A also. This is one more formula. Here, apart from the dimensions of a conductor, one more quantity which is going to influence the resistance value a lot. So that particular quantity we can simply say it as temperature. So temperature will plays a vital role. Even in the Ohm's law condition also, we will take temperature as a constant. Before we are going to proceed into that Ohm's law the Ohm's law properties and Ohm's law derivation and everything, by the time what we are going to discuss, the temperature of that particular place is constant or the temperature of that particular equipment is constant, or else the values are going to change. The reason for that one is if temperature varies, obviously the resistance value is also going to vary. So for that we have a simplified representation. What is that? For example, if RT is the resistance after a particular temperature, then we can write the relation as RT is equal to R naught into 1 plus alpha T2 minus T1. This is resistance after a particular temperature. Otherwise we can take as R2 or also you can take. So RT is equal to R naught into 1 plus alpha T2 minus T1. Very important formula. The same thing you can apply to that resistivity also. So rho T is equal to rho naught into 1 plus alpha T2 minus T1. Very important formulas. So these are the things. In addition to that, we have one more, that is color coding of resistors. So in general, resistor consists of different color bands. Each and every color band, it is having a particular value. So and importance also. So based on the color bands that are given on the resistor value, you can easily calculate whatever may be the value of the resistors they have given. Okay. So these are some of the important things that we have to discuss in case of this resistance and resistors. So each and every individual quantity is much more important while we are solving a problem, or even in the CBSE point of view also. Some questions they are going to ask in an indirect version. So on that particular case, we have to keep all these things in our mind while we are solving. Okay. So this is for today. This is an important concept, and each and everything we are going to discuss in detail. Thank you so much. If you have any doubts or any queries, or if you have any complaints on this particular concept, you may comment it. Thank you. Bye.